Hi, I am Kinsukacharyya from Physical Research Laboratory, India. Today I will talk about formation of molecules on the surface of the dust grains using chemisorption. I will give some examples in which the chemisorption can be important. So please bear with me in the introductory slides if I repeat something, because since all talks are pre-recorded, so I will not have luxury to change my slides or even my statements. So let's begin. So we know the our universe is molecular. So astronomical environments are filled with a lot of important molecules. So a question is asked how these molecules are formed. So by now, I am sure you have realized that they are formed on the gas phase or in the surface of the dust grains. So if you just take about the example of interstellar medium, which is nearly 99% gas and 1% dust, and the temperature is very low in this ISM, but still, if say two species I and J, they will eventually collide, and they will have a kind of a cross section for forming something which is in the order of 10 to the minus 12 multiplied by their densities. So this number looks very small, but considering the lifetime of the sources, these reactions are very much possible. But this is only the part of the story. So it was realized, like several molecules, most important, the most abundant molecular hydrogen cannot be formed efficiently in the gas phase at low density. So people successfully invoked their formation on the surface of the dust grains. Since then, the grain surface chemistry is an essential part of any astrochemical model, and there's a lot of molecules like methanol, water, they're very efficiently formed on the in the surface of the dust grains. So now, if you look at any astrochemical network, so it is evident that it will have two components. One is the gas phase reactions and other the grain surface reactions. And in the gas phase reactions, you will have primarily two components. So one is like low temperature reactions and others are high temperature reactions. These low temperature reactions will be primarily ion molecule reactions, and these high temperature reactions will be having reactions which have some activation barrier. Therefore, they are not possible at the low temperature. But besides, there are of course a very large class of various different types of reactions are possible in the gas phase, and they are incorporated in the chemical network. On the dust grain, although we only have low temperature reactions in most astrochemical models. So what is that? Basically, the species are bound to the surface via physisorption, that is via weak van der Waals forces, and in this scheme of things, the multi-layer is possible, and these are possible at low temperature, and you can see that in the interstellar medium, like it is dominated by formation of hydrogenated species like water, methanol, ammonia, and of course also complex molecules. But now the question comes, if these grains are heated, say around say 200 Kelvin, can we form something? And of course, we found out, and of course there are this also people studied formation of H2 earlier, that if we can invoke chemisorption, that is the species are bound to the surface by chemical bonding, then we can form molecules at high temperature. So this is the main topic that I will discuss in this talk. That is how molecules can be formed via chemisorptions, and whether this process can produce anything. So that will determine that whether this process is important or not. So before come to that, so let us give you some example of physical conditions in which there must be hot dust grains. Here by hot I will mean say around say 200 Kelvin or so. So if you just look at the star forming region here, so I have shown the density and temperature, and these are rough numbers and schematics. So uh, they're not, they are not exact, I would say. So if you just look at the diffusion transition cloud, so you will see that the H2 formation is the most dominant. That is formed on the surface of the dust grains. So now you come to the dense clouds or the pre-collapse phase. The grains are like 10 Kelvin. So they are primarily dominated by formation of water, and of course you also form ammonia, methane, methanol. Now when these grains are heated, say like around 30 Kelvin, so a lot of radicals start to move. So you also form complex molecules. Now, if you heat this grain further, say around 200 Kelvin, the entire mantle will sublimate. So grain is once again bare. So this is how we started. That is the bare grain, which is gradually mantles are formed, but then at high temperature, once again this mantle is gone. So now, can it take part in chemical evolution? So that is the question we are asking. So basically, even in the star forming regions, in the during this star and planet formation process, we'll have grains which will have temperature around 200 Kelvin or more. So now we'll give another example, like the AGB stars. So this is just once again a schematic. So here I have shown the temperature variation very roughly. So you will see that this kind of region where the dust formation occurs. And now if you just look at this region, like green shaded region, so here also we will see that the dust grains will have temperature in the range of say few hundred Kelvin. So now once again we can ask the same question: can these hot grain participated in the formation of molecules in these environments? So let's now move on to various processes that we need to consider if you have to use chemosorption. So this is very similar to the physisorption, though all the processes that we consider for physisorption will also consider for chemosorption, but we will make necessary changes because these are high temperature phenomena, and so there will have certain aspects that we need to consider. So of course the first step would be the adsorption, like resorption, but here we will see that the adsorption could be associative or it can also be dissociative. For chemisorption we have to consider both. That is, and when you consider dissociative, the one species can dissolve, that is, that can evaporate, they can come out of the grain surface, or both can stay on the surface. So once they are on the surface, we of course will consider their diffusion, and in the process they can form a new species or a separate species. And we can also consider like irradial mechanism, that in which a gas species directly land to a chemisorptive species and they form another species. And also we have to consider thermal and a host of non-thermal desorption mechanisms that are people regularly consider in the physisorption, in the formation of molecules via physisorption. We also have to consider photodissociation. So we consider all the major processes that are considered, or that are part of a grain surface chemistry at low temperature. So now let us move on further. So first I will start with the formation of H2. So these authors studied formation of H2 via chemisorption using rest equation approach. So they have considered both the physisorption and chemisorption sites, and they have considered the hydrogen can move from one type of site to the other type of site. So they can not only move on P2P site, but they can also go from a physisorption site to chemisorption site, or they can also come back from the chemisorption site to a physisorption site. But all the processes will have probabilities which are different, and they will be temperature dependent. That I will not come into the details, but you can look at these papers. They're very nicely discussed there. But as you know, that the formation of any molecule, you need sufficient number of molecules, the species on the grain surface. Say, for example, to form H2, we need at least 2 H2 on the same grain. So, but as you will see, when the temperatures are high, so you'll find that they are finding 2 species on the grain surface will reduce, their probabilities reduce. So what will happen? So we have to actually use a kinetic Monte Carlo kind of approach. So that is what we have used, and we have shown that the efficiency can be meaningful up to around say 700 Kelvin, and also it will depend on the depth of the chemisorption potential. In this context, I will also mention that we have studied this, extended this concept, the use of chemisorption, so for a host of other molecules. But in this study, we have only considered P2P or C to C movement. So not from P to C or C to P species. So that I just wanted to mention in this case. So this is the major difference between these two studies. So now let us see some, I will show just one slide for H2 formation. So in the y-axis, we have efficiency of H2 formation, and in the x-axis, we have temperature. So what we can see is that, so here we have plotted the efficiency as a function of temperature for few different models, and these models differ by the depth of the potential. So you can see if the chemization potential is 1000 Kelvin, which is a 10,000 Kelvin, that is for olefin. So you can see the efficiency is high up to around say 300 Kelvin or so. So now if we increase further, which is for say olivine carbon, which will be higher, the chemization potential. So you can see that it can be extended up to more than 400 Kelvin. If you use even deeper potential oils like 30,000 Kelvin, so it can be extended up to 700 Kelvin. So this slide also shows that there will be large difference or large overproduction or the large if we consider rate equation approach. So one must use the Monte Carlo approach for H2 formation, because that is in the low density region where in the ISM it will not have enough number of the probability will be low. So now let us move to the more complex molecules. These are more complex with respect to the hydrogen, not the standard complex molecules or compounds that we discuss. So now let us see that in this case, what we found is that most important parameter that we found is the adsorption barrier. So here in this plot, what I have shown is that in y-axis I have plotted the F coverage, that is the portion of the grains that are filled, and in the x-axis I have plotted time, and this is plotted for various models which are run at different temperatures. First of all, you can see that there is a temperature difference. I will come that little later, but first important thing is that if we have a adsorption barrier which is 0.3 electron volt, which is we found could be the highest, but of course one can find if could be the highest. So in that scenario, the only say 0.2 to 3% of point grain is filled. So now if we reduce the adsorption barrier, you can see that around 20 to 30% of can be filled. So the minimum adsorption barrier we have used is like 0.1 electron volt. So in that scenario, the grain can be completely filled. So we would prefer that there will be some activation, the barrier for adsorption for chemsorption. So the lowest we have used 0.1 electron volt. But of course, if you use 0, then of course it will be even larger, but that we didn't want it to do because we expect some barrier for adsorption. So now let us see the CO. So once again, you can see that this is for 0.3 electron volt, and you can see that C is actually, as you increase the temperature, so you can see this efficiency goes up. So you have little higher up to say around say 225 Kelvin. This starts increasing, but if you increase further, they will start to dissolve, and so basically your abundance will go down. So now similarly, if you once again reduce the adsorption barrier, you can see that you can produce more CO, and if you go to 0.1 electron volt kind of a adsorption barrier, the abundance is much higher. So this is close to the known as 6 region. So which is of course close to the detection limit for ice formed via physisorption. So now in this plot, I have plotted some of the carbon bearing species. So here I like to mention, just to point out that just look at the C2H2, which we found will have very large abundance that will be close to the 10 between the 7 to 6 for certain temperature range. And similarly, this is for nitrogen bearing species. For nitrogen bearing species, we found this ammonia, which is plotted in the black. So you can see that when the adsorption efficiency barrier is large, you only have like N is the highest. That's the atomic. So it just adsorbed and stayed there. It just uh, stayed there. So now if we have further increase the temperature, so it doesn't do much. So now if you reduce the adsorption barrier gradually, you can see that now you have a little bit more ammonia, and then finally you have a very large amount of ammonia. So we have also tried to see whether this formation of chemisorption species, when they will come out of the grain surface due to desorption, can they change the gas phase abundance? So let us see for CO. For CO, no, because you see that the CO abundance is significantly large, and the formation of CO via gas phase species is very efficient, so that the formation of CO via chemisorption will not change the gas phase abundance. But for C2H2 and ammonia, they can, whereas once again for HCN, they cannot. So now here we have also shown for warm-up models. You know the warm-up models, you evolve at low temperature up at 10 Kelvin up to certain time, and then your temperature is increased. So here I have plotted for two different models. Solid curve have like 0.1 electron volt as adsorption barrier, and the dashed line have 0.2. So here also once again we can see that like CO, and here we can see that also CH4, and then among carbon bearing species like once again like C2H2 here, this black line, and then for nitrogen bearing species once again ammonia. So we can see that there are few species which are forming in large quantities, and these quantities are large enough so that they are close to the detection limit of ice formed via physisorption. So if one can have the signature of chemisorption, the spectra for the signature of chemisorption of ammonia, acetylene, or CO, one can try to see that whether chemisorption is actually taking place in astrophysical environments or not. So now I will summarize the major results. So what we found is that the molecules can be formed via chemisorption, but of course the adsorption barrier plays a very crucial role. So if the adsorption barrier is low, then the abundance of chemisorption species is high. So if you have a species like CO, their gas phase abundance will not be altered because they are very efficiently forming the gas phase. However, the chemisorphed CO can achieve a reasonably high abundance of like 10 to the minus 6. Similarly, species like C2 acetylene or ammonia, they can also have a reasonably large abundance, but they can also alter the gas phase abundance because the amount of C2H2 or ammonia formed via chemisorption, they are more compared to the this formation of this species at gas phase at those temperature. Not only that, this abundance of this species is high enough so that one can try to find their signature via observation. There are many other species I have shown that like HCN, CH4, they have abundance between -7 to the -8, so which also have a large abundance. And of course, also we have shown for warm-up models. Here actually you have probably noticed that strip-like structure, and probably that is the artifact of assumption of that is the only monorail is allowed for chemisorption. But here we have few important note. These calculations are based on very scant existing literature and simplified assumptions. So more work is required, like quantum mechanical calculations and experiments required for extracting essential parameters such as diffusion barriers, sticking coefficients, and things like that. Here also we have only considered classical grains, but in principle one can do this study using a size distribution of grains. We also have shown our results only for star forming regions, but this work can also be extended for AGV stars. So if you want to have more details, please look at this paper. So I will stop here and take questions now.